Asynchronous real-time optimization of footstep placement and timing in bipedal walking robots by Digby Chappell, Wang and Petar Kormushev. We formulate the problem by considering the linear inverted pendulum model for bipedal walking. We use two optimizers. The RK4 optimizer uses a Runge-Kutta fourth-order approximation to the system dynamics to simplify the nonlinear optimization, which can be solved at 25 Hz. The gradient descent optimizer uses the full system dynamics with calculated analytical gradients and constraints reformulated as penalty functions to find approximately optimal footsteps at 250 Hz. These are combined as asynchronous real-time optimization, RTO. To combine the two optimizers, they are run in parallel. Each optimizer is initialized with the latest solution and robot state. This essentially allows the gradient descent optimizer to interpolate between RK4 optimizer solutions, giving quicker reactions to disturbances. Another major benefit is that there is redundancy in optimizer solutions. If one optimizer fails to find a feasible solution, the other can make up for it. To test the capabilities of RTO, it was compared against two other footstep planners, location-only MPC and the RK4 optimizer running alone. 3 experiments were performed. 1. A qualitative observation of small push recovery. 2. Finding the maximum possible push that can be recovered from in each direction. And 3. Finding the maximum possible reference velocity change that the planners can produce a stable footstep plan for. All experiments were performed in simulation on the walking robot Slider. As seen, location-only MPC cannot recover from a horizontal push without changing footstep location. This causes the centre of mass to deviate reasonably from its original trajectory. The planners that also optimise footstep duration, RK4 and RTO, can both resist the push by altering step duration, causing minimal deviation of the centre of mass trajectory. The maximum push force for RTO was considerably higher than for RK4 and MPC in all directions. Particularly important is the improvement over MPC in the sideways directions, where step location is constrained to prevent foot collision, so step duration optimization is favourable. RTO is able to react more quickly to the pushes, giving improved performance over RK4. RTO again outperformed RK4 and MPC in all directions when producing feasible footstep plans from reference velocity changes. For all planners, constraints on footstep placement in the coronal plane make it harder to react to larger reference changes sideways. Our key findings are this. Optimizing footstep duration greatly improves push recovery and response to reference velocity changes. Even RK4 running at 25 Hz was able to outperform MPC running at 500 Hz. Using gradient descent to interpolate between more accurate solutions improves velocity reference change capabilities and significantly improves push recovery. In particular, RTO is significantly better than RK4 or MPC when footstep location is constrained. Finally, we present 2 further applications of this RTO footstep planner. On the left, we demonstrate that by only varying the reference velocity, we can achieve a form of agile locomotion. On the right, we show that by applying a varying force on the body of Slider, RTO will step to compensate, giving a novel way to control a walking robot.